Hi, welcome to my presentation for Physics 2212, Lab 4 on circuits and capacitors. In this presentation, I will introduce the experiment and explain some fundamental physics principles, discuss the experimental models, and conclude by answering some additional questions. To begin, the purpose of this experiment was to predict the behavior of circuits containing resistors and/or capacitors in series and parallel circuits. The purpose is also to measure the values of the conventional current and the potential differences in circuits using a multimeter. In this experiment, we're assuming that the CCK simulation used correctly reflects conditions associated with its real-world equivalents. We found that the value of I for this experiment was 0.02, and that the value of RC was about 6 seconds. Theoretically, exactly 6 seconds, but our experimental data was right around that. So to explain some key fundamental physics principles important for this experiment, three super important ones include Ohm's rule, Kirchhoff's loop rule, and the node rule. Also, potential difference of a capacitor, capacitance of a capacitor, and the RC circuit equation are also important, and the equations for all of these can be seen on the right side of the screen. Each of these physics principles come into play in this experiment, as there were multiple steps and aspects to this, but in particular the loop rule was important, which states that the total voltage of a looped circuit should equal 0. So the first step in our experimental model, working with series circuits, was to predict the current at different locations in this circuit that would be measured by the two ammeters. And so we could find what this value should be theoretically, which is 0.02, and then using the simulation we found that the reading actually ended up showing 0.02 as well. So those two matched. Also discovered that reversing the connection to the ammeter didn't change the reading either. Next, I replaced one of the ammeters with a voltmeter, and so now the reading on the ammeter was 0 because the circuit was open and there was no current flow. The voltmeter still showed 3 voltage because it was displaying the potential difference across the battery, and that total change in V did not equal 0 because the loop wasn't complete. Next, I measured the potential difference for each part of the path around the circuit in the diagram shown on the right. And the values of those different paths are shown on the right side of the screen, but the important thing to note is that it ended up equaling 0 volts, which is what we would have expected based off of Kirchhoff's loop rule. And I've also included a graph to show how this potential difference was mapped over time as well. Next, I placed another ammeter in parallel to the 100 ohm resistor, and the reading changed from 0.2 to 0.6. But we can also prove this theoretically, mathematically, with the equation shown on the screen. That explains why this change in the circuit exists. Next, I made a graph that talked about the different values at the different points, including the change in voltage and the I and R values as well, and all these are listed on the screen. Next, we switched to working with an RC current containing a light bulb, battery, and a capacitor. When you connected the whole thing together, the light bulb illuminated brightly at the beginning, but then the light faded out. And then if you disconnected the battery and connected the capacitor right to the light bulb started out bright as the current flowed in the opposite direction and then decreased until it turned back off. After this, I measured the time it took for that charge and discharge to happen for the different ohm light bulbs, the 10 and the 20 ohm light bulbs. And because the 20 ohm bulb had about twice the resistance of the 10 ohm bulb, I predicted that the time to charge-discharge should be about double. And this was shown in the experiment. They're right about double the amount of time to charge and to discharge between the two. Next, I worked with a time-dependent voltage across the discharging capacitor. So I set up the simulation in the CCK simulator and measured the voltage across the capacitor with a voltmeter, and set the capacitor to discharging and plotted 20 seconds worth. And that plot can be seen here on the screen. And that goes in a negative direction, which also makes sense based off the equation that we saw at the beginning of the presentation dealing with the situation. And so it made a nice line that we would have expected based off of the information given. So to conclude, I found that the value of I in the initial part was 0.02, and then after plotting the information that I collected from the second step, I found that the equation of the line was y equals negative 0.0667x plus 4.44 e to the negative 16th. There wasn't a lot of potential source of error because it was all a computer simulation, but potentially I could have done a mathematical calculation errors, or with the stopwatch, I also could have had some error there when I was making or gathering my data points. And now some additional questions to consider. What if an actual ammeter had been used as the ideal simulated ammeter? Well, it likely wouldn't have displayed 0 ohm resistance because the overall current in the reading would be lower than the ideal value predicted, because current is inversely proportional to the equivalent resistance. Also, if a real battery was used to charge a real capacitor with no resistor in the circuit, the capacitor would be charged immediately. But in real life, all circuit components have at least some slight resistance, so it would still take a few instances to charge the capacitor. It wouldn't happen instantaneously. Thank you so much for watching, and have a good day.